Hello everyone, today my topic is Enhanced-XGB, an online service resource demand forecasting method for colocation data centers. We will introduce our works from these 5 aspects. The first are the background. Colocation, which can effectively improve resource utilization by co-locating online service and offline tasks in the same data center, is being adopted by more and more large-scale data centers. The key point in co-location is how to schedule offline tasks to reuse idle resources as much as possible while ensuring the SLA of online service. For this problem, one of the solutions is predicting the resource demands of online service, then scheduling offline tasks based on the prediction. In this method, predicting the resource demands of online service is one of the most critical issues. There are lots of service instances in data center. A general practice is clustering the containers of online service first and train prediction models for each cluster. Cluster-based resource demand prediction is still far from trivial. Four challenges must be considered. First, determining efficiency. Numerous resource usage data will be collected to train model. Therefore, the model should be able to learn patterns of data efficiently. Second, adaptability to complex environments. Various online services would be deployed, and at the same time, service upgrade and configuration modification are common in data centers. It requires the model should be able to give reliable prediction results in such a complex environment. Third, real time. We need time to schedule offline tasks, so the model should give the prediction results fast. The last one, trade-off between accuracy and cost. In practice, both prediction accuracy and expenses will be taken into consideration. Existing prediction methods can be broadly classified into 3 categories: statistical, machine learning, and deep learning. Statistical methods, such as moving average, is simple and efficient, but cannot handle the complex situation. Machine learning methods are widely used due to great interpretability and high prediction accuracy, but they are weak in dealing with the inconsistent environment. Deep learning methods can achieve great results, but have large computation costs and usually difficult parameters tuning. Among existing models, XGBoost, which has great computational efficiency, fast computing speed, and well prediction accuracy, while maintaining low training costs, is an ideal model for data centers. However, its prediction error will increase sharply when range drift presents. In data centers, the patterns of a long-running container may be quite stable, but the data range may change sometimes. That makes sense, since configuration modification and service upgrade are general in practice. As shown in this figure, the general pattern of time series in containers remains unchanged, but the data range of them tends to increase or decrease significantly. We call such a change of data range as range drift. XGBoost is a tree-based model. Due to the model architecture, outputs of XGBoost are constrained to be within a certain range, in fact determined by training data. We cannot guarantee that training data can cover all situations. If range drift occurs in testing data, XGBoost model will suffer and its prediction accuracy will decrease significantly. To address this problem, we propose a new model named Enhanced-XGB. Before introducing the details of model, let's see how our model works. In training phase, all containers will be normalized with zero mean, then are clustered with using k-means. For each cluster, an Enhanced-XGB model will be trained. In testing phase, data of each container will be sent to model separately. After normalizing and classifying, a corresponding model will be used to predict the resource demand. As for the details of Enhanced-XGB model, this figure shows our model architecture. Enhanced-XGB consists of three major parts: attributes, coefficient CNN, and offset CNN. The attributes part is the same as the original attribute model. While training our models, we first build a normal attribute model to get the sample of trees. In the attribute model, new trees are created to correct the residual errors in the prediction from the existing sequence of trees. In other words, different trees match the information in the data at different levels. Based on this point, we can assign different weights to different trees based on the hidden pattern of the input to further improve the prediction accuracy. Convolutional neural networks are usually used to extract features from data with high computational efficiency based on parallel convolution operations. Therefore, we designed the coefficient CNN that consists of a convolution layer and a linear layer. The convolution layer, determined by its filters, is used to capture local dependency, while the linear layer maps the extracted feature to weights. In this way, coefficient CNN can dynamically adjust the weights of trees in the attribute model. Besides dynamically adjusting the weights of trees via coefficient CNN, we also train an offset value for the final weighted sum via the offset CNN. Similar to coefficient CNN, offset CNN is also composed of a convolution layer and a linear layer. However, different from coefficient CNN, which captures local dependency and is independent on the relative position in time, offset CNN is completely independent on the position in time. The final prediction result of our model is the weighted sum of the outputs of trees plus the offset value. We also deployed the Enhanced-XGB model in practical data centers. In Tencent Game, there are tens of thousands of physical machines running hundreds of thousands of containers and supporting hundreds of games at the same time. Online service here mostly refer to online games, while machine learning tasks of game AI are executed as offline tasks. To improve resource utilization, a colocation system named Vertical Workload Autoscaler are designed to collocating online service and offline tasks. VWA consists of three major parts: recommender, local updater, and extender scheduler. Recommender makes use of historical and real-time resource utilization type data to calculate recommended values. Local updater adjusts the resource request of containers in place instead of recreating pods. Extender scheduler is designed to schedule offline tasks, which reduce the idle resource of online service. Our model is integrated as a part of recommender by replacing the original prediction algorithm with Enhanced-XGB. To ensure QoS of online service, a safety margin will be added to the prediction results as the final recommended values. We conduct experiments to evaluate our model. The trace used are samples from one of the production data centers in Tencent Game, which have 1,074 containers running online service. Four types of resource utilization data are recorded: including CPU, memory, network inflow, and network outflow. Each container has 4 time series in 14 days periods with a 30-second sampling interval. We divide the data into 3 parts: 10 days for training, 2 days for validating, and the last 2 days for testing. Mean absolute percentage error (MAPE) is used to measure the performance of prediction models. Each container will produce a MAPE result. We pay more attention to the average, maximum, minimum, variance, and percentile of the matrix of all containers. The average and percentile reflects the overall prediction accuracy of the models, while the maximum, minimum, and variance report the prediction stability of models. A stable prediction error will help narrow down the safety margin and consequently save resources allocated to online service. The k-means algorithm is used to cluster all containers. The specific information of clusters is shown in this table and figure. We evaluate our model and compare it with attributes and LSTM in 2 modes: univariate and multivariate. Univariate means that models only use the historical CPU time series of containers, while multivariate means that multiple time series of containers are simultaneously used to train and test models. As shown in this table, our model outperforms STM and attributes in most matrix indicators under both univariate and multivariate, especially in terms of the maximum and variances. With better prediction accuracy and stability, our model is more suitable to apply in critical data centers. To show the effectiveness of our model in handling range drift, we conduct experiments on a container with no range drift in univariate mode. The time series before the range drift is used as the training data, while the time series with the range drift is used as the testing data. As the result shows, attributes model achieves good results before the range drift occurs, but gets poor performance after due to its model structures. As for the Enhanced-XGB model, it performs as expected all the time. Such a difference clearly shows that our model can predict the resource demands of containers with range drift, which makes it more powerful when predicting in real data centers. In conclusion, in this paper, we propose Enhanced-XGB model by dynamically adjusting the weights of trees in attributes as well as an offset value with convolution networks. Our model can handle range drift of data so as to achieve high prediction accuracy and high adaptability for critical time series in large-scale data centers. The proposed model has been deployed in real production data centers at Texas Games. Experiment results show that Enhanced-XGB performs well, produces accurate predictions, and outperforms existing ones. In the future, we will exploit the scheduling algorithm combined with prediction and more effective clustering method to further improve the performance of colocation technology. And that's all. Thanks for your listening.